Hello. Today we'll take a look at section 1.9, Polynomial and Rational Inequalities. So we'll learn how to solve each of them. A polynomial inequality is made up of many terms separated by addition and subtraction signs. To solve a polynomial inequality, such as the ones you see here are the steps that we're going to follow each and every time. First thing is to put it in standard form. So we're going to move everything to one side, leaving 0 on the other side. We're going to put everything in descending order of powers. We're going to factor the inequality that's on the left-hand side. And once we factor it, we're then going to set each of those factors that contain a variable equal to 0 so that we can solve for what we call boundary points. We're then going to label a number line with those boundary points, those solutions that we found from step 3. We're going to label those numbers on a number line, and we're going to place a closed circle or an open circle above each number based on the inequality sign of the problem. Remember, less than or equal to, greater than or equal to means that it includes those endpoints or boundary points, so we use a closed dot or closed circle. Less than or greater than means it does not include those endpoints, and so we use an open circle over those values. Those boundary points are going to divide our number line into different intervals. We are going to then choose what we call a test point from each of those intervals. It can be any number that falls within that section of numbers on the number line, within that interval. You pick your test value and you plug it back into the original polynomial, and you are looking to see whether or not the value you get is positive or negative. You will then label your number line with a plus or minus sign to indicate that you got a positive or negative value when you chose your test point and plugged it in. Finally, step 7, you're going to choose the intervals on your number line that satisfy the given problem. So for example, if we were looking for things that are less than or equal to 0, that means we were looking for things that were negative, and so we would choose that section of the number line to represent the solutions to that problem. If we were looking for something that was greater than 0, well then we're looking for things that are positive, and so we would select the portions of the number line where we placed a plus sign to indicate we got positive values. Let's take a look at an example. Problem number 2 from your book is written here. Notice everything is already on one side of the problem, 0 on the other, so step 1 is taken care of. Notice that the problem is actually already factored, so step 2 is done. So what we're going to do now is actually set each factor equal to 0. So we end up with x equals 0, and we end up with 3x plus 2 equals 0, and we solve and end up with two values for x, 0 and negative 2/3. So notice I labeled them on the number line. Be careful to label them in the correct order in which they would appear on the number line. So of course negative 2/3 appears before the 0. Once you do that, go ahead and place the correct dot over the numbers. So because this was less than or equal to, we used a solid circle or closed circle over each number to show that we can include those in our solutions. Alright, so now my number line is divided up into 3 intervals, 3 sections. We're going to choose a test point from each of those sections. So in this first interval here, I can choose any number that is less than negative 2/3. I went ahead and chose the very next integer, which would be negative 1. You take that negative 1 and you plug it back into the problem. So I have negative 1, parenthesis, 3 times negative 1 plus 2. So I'm plugging it back into the problem. When I simplify what's inside the parentheses, I get negative 1 times the negative 1 outside, so I end up with a positive number in the end. So I put a plus sign to indicate that pretty much any number you pick in this interval is going to give you a positive value. Then we chose a test point in this location here, between negative 2/3 and 0. So I chose negative 0.5 or negative 1/2. Plugging it into the original problem, 0.5, negative 0.5, parenthesis, 3 times negative 0.5 plus 2, that's how I have what I have here, when you simplify it, you get a negative 0.25. So we got a negative value. And that's what we're concerned with right now, is whether or not it's positive or negative. So that's what we label this entire section will generate negative values. Over here, anything greater than 0, I chose 1. And when I plugged it in, I got a positive 5. So I labeled that positive. Looking back at the original problem again, remember it was less than or equal to 0. So we were looking for things that would make the problem negative. And that would be this interval of numbers here. So we're going to express our answer in interval notation. So because the closed dots indicate the endpoints are included, we put a bracket, negative 2/3 to 0, bracket. These values make the original problem negative, less than or equal to 0. All right, take a look at another example, number 8. Notice in number 8, it's not in standard form. Everything is not on one side, so we begin by doing that. So we're going to move everything over to one side of the problem. And so we did that by subtracting the 24x and adding the 2x squared, putting everything in order of descending exponents, descending powers. And then we are looking at making everything greater than 0. Since once we moved everything over, we had greater than 0. So we're looking at making things positive when we select our final answer. So what we did was then factor the left side. There's a GCF of 2x, so we take that out first, leaving this trinomial. So we divided each part here by 2x. Then we continued to factor this trinomial, and we ended up with x plus 4, x minus 3. We then set each factor that contains a variable equal to the 0. Notice we have 4 different factors here. So we set the x equal to 0, the x plus 4 equal to 0, and the x minus 3. So we ended up with 3 boundary points. We then labeled the number line with those 3 boundary points in order that they would appear on the number line. So of course negative 4 first, 0 next, and 3 next. Notice we put an open circle over each number because this was strictly greater than, so we weren't including the boundary points. We then chose a test point in each of those intervals. We have 4 different intervals now on the number line. Any test point is fine, as long as it's less than negative 4 in this example. So I chose negative 5, plugged it into the problem, so 2 times negative 5 to the 3rd power plus 2 times negative 5 to the 2nd power minus 24 times negative 5. I got a negative 80. So I labeled the top of my number line with a negative sign. Here I chose the test point of negative 1, plugged it in here in the green color, and I got a positive 24. So I put a positive sign. Here I chose to test the number 1, plugged it in. When I plugged in a 1 here, here, and here, I ended up getting a negative 20. So I placed that there. Here I chose to test the number 4. I plugged it in for each and every x, and I got a positive 64, so I labeled that with a plus sign. We were looking for values that would make this greater than 0, so we were looking for the positive areas. So that would be this section of numbers here, which we would write in interval notation as negative 4 to 0, parentheses on each end, as well as this section here, so that's why we have union from 3 to infinity, because we would continue this all the way to the right. And so this represents our solution set to this polynomial inequality. Any of the numbers you pick in this range or this range would give this a value that is greater than 0. Now we're going to take a look at solving rational inequalities. The process is very similar. We first begin by moving everything to one side so that we have a 0 on the other side. We then factor the numerator and denominator, and we set each of the individual factors that contain variables equal to 0. If there are any common factors, you would go ahead and cancel them. And if you have 2 separate terms, you would first go ahead and rewrite it as a single fraction with a common denominator before you start factoring. So once again, step 1, you move everything over to one side, you have 0 on the other. You combine terms if necessary to create a single fraction. You factor the numerator and denominator of the fraction. You cancel any common factors there that it may contain from the top and the bottom, and then you set each factor in the numerator to 0, each factor in the denominator to 0, and that's how you find your boundary points. You then label those boundary points on a number line. Now, once again, we're going to use a solid circle for these inequalities, an open circle for these inequalities. However, any boundary points that you find from the denominator, remember, we don't ever want the denominator of our fraction to be 0 because it would be undefined. So if you find a boundary point from the denominator of your problem, you're going to always use the open dot over that boundary point. No matter what the inequality is, you want to use an open dot so that you don't include that particular value in the solution set, because you know that that value would make the denominator 0, which would make the problem undefined. Step 5, you then choose test points just like we did before in each interval. You plug it into the polynomial and you see whether or not you get a positive or negative value. You then label your number line with a plus or minus sign. And finally, step 5, you choose the values that satisfy the inequality. Now, in a problem such as this one, it might be very tempting to say, why don't we just go ahead and get rid of the fraction by multiplying both sides by x minus 2? We can't do that in an inequality because we don't know if x minus 2 is positive or negative. Therefore, we don't know whether or not we would need to reverse the inequality sign when we multiply both sides by it. So we can't get rid of the fraction, we'll have to work with it. So as I was saying earlier, what I would do is get a common denominator, which in this case would be the x minus 2. And so we multiply top and bottom here by x minus 2 and use the distributive property. This is what we would get. You could then factor the numerator. This is what you would get. And then you would proceed with the steps that we just mentioned. All right, let's take a look at this particular problem, number 14. So we do have everything on one side, 0 on the other. We're going to go ahead and factor the numerator. Notice it's the difference of 2 squares. There's nothing for me to cancel. So what I'm going to then do is set each part of the numerator equal to 0, each factor that contains a variable, and each portion of the denominator equal to 0. And so I end up with 3 values. I labeled those 3 values on the number line. The ones that I got from the numerator, notice, have solid circles over them. The value that I got from the denominator has an open circle over it. Even though this inequality would indicate I could use a closed circle, we use an open circle over every value from the denominator because we don't want to include it in the solution set because it would make the problem undefined. So we now have 4 intervals to test. You choose a test point, you plug it into the problem, and you see whether or not you get a negative or positive value. So these are the test points that I chose. I've circled each one of them. This time when I worked out the problem, instead of actually calculating the value all the way, I just wrote down whether or not it would generate a negative or positive. So for example, negative 4 plus 3 would be a negative number. So I just put a negative sign. Negative 4 minus 3 would be a negative number. Negative 4 plus 2 would be a negative number. So negative times negative on the top would give me positive. Negative on the bottom, positive divided by negative would give me a negative solution. So this is just another way that you could do the problem and still come up with the fact that you got a negative value. Or you could actually plug the numbers in as we did in the other examples and get it that way. So just wanted to show you an alternative. So I test each of these points, and these are the positives and negatives that I came up with. The problem was looking for things that made it less than or equal to 0, which is negative. So that meant this interval here and this interval here was going to be my solution. So notice the interval notation, negative infinity to negative 3, inclusive, and then from 2, notice negative 2, the parenthesis, all the way up to the 3, including the 3. So that is how we would solve rational inequalities.